So, continuing with our discussion on coke quality, today is lecture 4. I started discussing this topic yesterday, and when I was about to finish my lecture, I talked about the coke strength upon reduction, how actually gasification reaction tends to, help producing cleavage and breaking down of the coke in the upper stack region itself. So, to complete the discussion, there are 5 essential qualities of coke which are taken into account when a given coke is selected for introduction into a blast furnace in the iron making circuitry. So, this first and the most important is the chemical composition, and I would say that of this, perhaps the most important is the fixed carbon content of the coke, which determines its calorific value. And we must understand that coke upon combustion, just like coal also, will leave behind some residue, and these residues are basically silica or siliceous compounds with some calcium sulfide, etc. So, smaller is the fixed carbon content, greater is going to be the impurity elements which we call as a gangue material in the coke. So, that is not desirable. So, higher is the coke, more is the effective utilization of the furnace, because otherwise you are charging into the furnace something which is not carbon but something else. So, which means the furnace is filled with garbage material and not the one which is really needed, and that is coke. The second point is the reactivity of the coke. If the coke has very dense structure, in that case its reactivity is affected. So, we require a cellular structure of the coke so that it has a reasonably high reactivity. Okay? The surface should not get poisoned, etc. So, the coke should be readily combustible, because we are not introducing powder of coke into the blast furnace. We must understand we are using certain specific size ranges. So, therefore, the lump coke must have good reactivity, that is essential requirement. The size and the size range of the coke is also very important for what we administer into the. Now, as we require not too much of a variation as far as the size range is concerned. We cannot of course administer one single size. So, there is a range of. So, the mean size has to be close to the one which is prescribed. I will tell you about that in a minute, and it should not have too much of a variation from that mean. So, it is a small variation in the size range, and we must understand that as far as the blast furnace material goes, you can imagine that if you have a volume like this and you fill up with 4 different particles as opposed to big particles, as opposed to a system, the same system where you are filling up with maybe several small particles. Okay, you must understand that smaller the particles, okay, you are going to have all the pores, and if you have wide range of sizes, then what happens is the smaller particles like this will come to occupy the voids, and that we do not want to happen. So, we want really a narrow size range, that is what is our, so that if the size range is too big, in that case the small particles will get inside the big particles, as I have shown here. Also, we must understand neither we need a too big a particle. If you take too big a particle, then what happens is great big portion of the domain is going to be filled up with the particle itself. So, this is our the domain of interest, and I have put in 1, 2, 3 and 4 particles, and you will find by putting 4 large particles into this volume, I have bulk of the volume remains, a good portion of the volume remains unutilized. So, therefore, if you think of this volume to be a furnace or the blast furnace, you must understand the bigger is the size of the particle introduced into the blast furnace, smaller is going to be the effective utilization of the blast furnace volume. On the contrary, but in this case the voidage is going to be very, very large, and if the VC represents the chamber volume, which is L in this case you can say this is length into breadth into height, that is what is the, if the chamber is like this, So if Vc is the chamber volume, then we have, and Vs, if you have equal size particles, then if this is the volume and this expression applies, where E epsilon represents the voidage of the system. So we can understand this parameter. So is going to be, because the volume of the spheres are going to be much smaller, each volume, so there the porosity, because the same volume element we are considering of the reactor volume or the chamber volume is constant in both the cases. So smaller is the particle size, larger is going to be the smaller, because you have more number of particles. So in this case you are going to have lesser volume actually of more space is going to be the volume of the solid, is not the individual volume of the solids, but it is the total volume of the solids, that is what it is. And then this parameter here, the total volume of the solids is going to be larger, smaller than the total number of volume, and as a result of which the E1 here, the voidage, is going to be greater than E2. So in the limit of very small particles, therefore we can understand that the blast furnace bed permeability will be 0, okay, and in that case the gas will have difficulties in going out. So we say that there is a standard schematic representation that if we take particle size and we plot productivity, we will come back to this when we talk of productivity, how is blast furnace productivity. The curve goes something like this, indicating essentially that there is a critical particle diameter for which the furnace volume utilization is good, for which the passage of the gas is good and the voidage is good, and this particle size gives the optimum bed porosity and optimum utilization. So neither too large a particle nor too small a particle is going to be beneficial for blast furnace, and that is what I said, that the size range should be narrow, okay, and we should have a mean size, and we must understand that as the iron ore particle will descend, its size is not going to change much within the blast furnace, except perhaps for the thermal expansion part of it. Okay. On the other hand, the coke particle is going to be reducing in size, mostly because of the solution loss or the gasification reaction which takes place in the upper part of the blast furnace. So let us, so that you can visualize my lecture better, so I think it is time for us to draw that schematic of the blast furnace and then show that, well, that is what it is. And then we have this. So the coke particles we are introducing, suppose if I say that I have a tolerable size range of 10 to 30 millimeter of all the solid particles, we must understand that up to this point, as the particle descends, the sizes are not going to change. So what we have here, we have iron ore, we have let us say iron ore sinters, etc. is combined iron bearing materials, we have coke and limestone, and if you use all these particles having the same size range, we understand that limestone does not undergo much degradation here or no reaction here in the upper part. Similarly, iron ore does not get reaction, but here what happens, the solution loss reactions are carbon plus CO2 is equal to 2CO. This reaction can take place here, and this can cause a reduction in the size of coke. So now, although the size range was quite tolerable or acceptable here, because of this reaction the size range here may not be that tolerable, and as a result of which what happens is, we say we charge the coke particle a little bit bigger size, so that we do not create too many small particles because of coke particles, because of this reaction which can jeopardize or impair the permeability of the bed. And finally, I would say the strength of the particle, coke particle, is very, very important, strength as well as the thermal stability, because the coke is going to be from here, as I have indicated in the stock line, about 500 degrees centigrade and come to the 2L level, and here we have something like 1900 or I would say 2000 degrees centigrade. So as the coke particle descends, the coke is expected to withstand this temperature also. It must not undergo, what do you call, liquefaction. It must not lose its plasticity too much. It should not undergo, much changes physically in terms of the changing temperature, and most importantly perhaps that when the coke material descends, the thermal shocks to which it is subjected to because of the changing environment and because of the strong current of the gas, the thermal stability is very, very important from that perspective. So, no degradation of the coke in this intensely changing thermal environment within the blast furnace, or as little change is perhaps desirable and as not. And most important is the physical strength of the coke, and which I have said that because the solution loss reaction is endothermic, and as a result of which what happens is that if you have the coke particle here and that this reaction will take place. What is this? This is a heterogeneous chemical reaction. One is this a gas solids reaction, and this gas solid reaction will not take place here in the gas phase. It can only take place at the gas solid interface, which is this particular interface that we are talking about. It is the gas. So, heat is going to be absorbed here, okay, because the thermal demand of this is being an endothermic reaction, and as a result of which, while the rest of the coke is going to be hot, this part is going to be cold, and this difference in temperature is going to introduce now thermal stresses in the coke, as a result of which delta T is directly related to the thermal stresses that is generated. Stresses generated in material due to differential temperature, and that differential temperature will take place because of the reason that this reaction is endothermic. So, from here what happens, that cracks etc. can originate, and because of the high flow of the gas we can have loose particles of coke coming out, and this is what is meant by the degradation of coke due to the gasification reaction somewhere around here in middle of the stack. And this coke should be able to, that even if the temperature gradation, this reaction we cannot stop in the blast furnace, but what we want, that as a result of such reactions we can minimize these reactions. Of course, we can, what proportion of direct reduction will take place, we will understand it a little bit later, but what is most important, that even though this reaction will take place in the blast furnace, this should not lead to any such phenomena whereby coke can disintegrate or fragment into a number of, even such cases what happens, the coke may develop fissures, and as a result of which further down the coke may disintegrate where the environments are far more hostile, and this we do not. So, all these parameters actually qualities are looked on or searched in a given good quality coke, and we must understand that all these qualities of coke will be fulfilled provided our starting material coal is good. And that is what I say, just like the slogan, from sharp mine comes sharp products, and here I say from good coals come good coke. Now, with this little background we will now stop discussion on coke, and we now move on to the iron ore part of. Limestone as such do not require much preparation. Only thing is that we have to understand that limestone basically contains calcium oxide, magnesium oxide, as well as silica. These are the predominant constituents of limestone, and when we buy limestone for blast furnace operation, we must understand that it contains only a permissible level of MgO and permissible level of, more importantly, silica as impurity. So, other than that, of course, limestone does not, once we have the size ranges, limestone will undergo calcination, and calcination will take place around 900 degrees centigrade, whereby limestone will decompose, and below this, above this, calcium carbonate will exist, limestone will exist as calcium carbonate, and below this line limestone will so this is similar phenomena, high temperature phenomena, but this is akin to loss on ignition when you heat a moistened material and the moisture gets out, but in this case carbon dioxide is chemically combined, so you have to apply energy in order to break the calcium oxide carbon dioxide bond, and that is facilitated at about 900 degrees centigrade, and below this you see the lime particle. Of course, the characteristics of the lime is important, but lime also we will not like to get fragmented, it should have good amount of strength, and of course the reactivity of the lime is also very, very important, and reactivity if it is a big size lump with not much of porosity, or in that case, because the lime has to, as we will see, the lime takes very important, the calcium oxide does has to react with silica, alumina, etc. in the lower part, that we will discuss later on. But it is sufficient for us to say that the limestone will exist above this 900 degree line as calcium carbonate and below this as calcium oxide. And as we say that we would like to have lime with moderate or good reactivity, we would like to have lime with good CaO content, not much of magnesium and silica content, and of course we have to satisfy this requirement that the size and the size ranges should not vary because of the discussion that I have just now presented. Coming to iron ore, now iron ore is produced in the the iron ore mines, and we all know, as I have indicated, that it is either we have, this is the most popular ore of iron, magnetite, this is hematite Fe2O3, and this is magnetite, and India we find predominantly Fe2O3, but there are countries where Fe3O4 is also available in abundance. So hematite is the basic raw material, I would say. We will start it, we will not consider Fe2O3, Fe3O4. So hematite is the principal raw material, and this is hills of hematite are available in many places throughout the country, predominantly, as I have indicated, in Madhya Pradesh, in Chhattisgarh, in southern India, Karnataka, for example, we have huge iron ore mines. These are not like coal mines that you have to dig inside. Okay, they are available. You have to just excavate. Okay, they appear as big hillocks, and it is said that these are mostly of meteoritic origin. So initially they are all iron, and then as the Earth's atmosphere started to have due to development of various biodiversities oxygen into it, these irons start getting oxidized, meteoritic iron, and then ultimately manifested in Fe2O3. If you do a theoretical calculation, just a stoichiometric calculation, you will find that in a pure Fe2O3 70% is Fe, remaining 30% is oxygen. Okay? And this is what we say, that a grade of pure hematite is 70% Fe. So we will say that what is the grade of your iron ore? You will say 60% Fe. Then we have a good understanding that what you mean, that you will have 60% Fe, corresponding to that 60% you will have some oxygen, you can calculate stoichiometrically, and the balance is going to be the impurity elements which we call as the gang materials in the ore. So 70% Fe is rarely available. This is a pure Fe, this is synthetically prepared. Natural Fe will never contain 70%, and natural Fe2O3, I would say very good iron ores are about 60 to 65%. That is the grade of a very good iron hematite ore, 60 to 65% iron. And the balance in iron ore is the gangue material. And what are these gangue material? These gangue materials are silica, alumina, titanium dioxide. These are the major ones, and there could be some other traces depending on their origin. Okay? We must now have a quick cursory look that Al2O3 is a very stable oxide in terms of blast furnace temperature range. If we look at the Ellingham diagram, for example, where we plot delta T versus delta G naught, and then we see that the aluminum line is somewhere like this from here. So I am drawing it schematically, okay, not so much of a slope, and then I would say, and then if you do the carbon monoxide line, and that line comes out to be something like this, and this temperature is about 2200 degrees centigrade. What essentially, so this is Al2O3 line, this is C line. So what does this indicate is that COCO, this is COCO2 line. Carbon plus oxygen is equal to carbon per mole of oxygen. All Ellingham diagram lines are per mole of oxygen. So you have to balance these equations like this. So this is, if you say C plus O2, then we say 2CO. So that means what does this indicate? That if you have below 2, this I think you have all studied this. What does this temperature indicates? That below 200 to 2200 degrees centigrade, okay, if you have oxygen, aluminum and carbon, oxygen will preferentially latch with Al2O3 or Al and form Al2O3. Above 2200 degrees centigrade, we say that the same oxygen will now latch on to carbon, because the free energy of formation of carbon monoxide is smaller, lower than the free energy of formation. So that is what the Ellingham diagram tells us actually. And you will see that the same line, for example, if you draw the iron ore line, something like this, it goes like, one line goes like this, the other line goes like this. This is Fe3O4 and this is, so FeFeO line, FeO Fe3O4 line, and Fe2O3 line does not come into the picture, it is far above it. So if you know what it indicates, that even a little bit of carbon monoxide will be able to reduce Fe2O3 to Fe3O4. In my first class I have said that iron ore undergoes reduction in several steps. And these are the steps in which the iron ore undergoes reduction. Okay? So, these impurities, coming back to the impurities here, this Al2O3 for example will never undergo any reduction as far as the Ellingham diagram is concerned. So, Al2O3 from Ellingham diagram we conclude is going to be stable oxides under blast furnace. So, this Al2O3 is going to remain as Al2O3 and we will see where it will go eventually. On the other hand, the silica can get reduced, the line of silica reduction, silica line is in between the two, and this could be somewhere around here and this could be something around 1600 degrees centigrade or so. And this temperature is an attainable temperature in the blast furnace. There are some regions where we have 1600 degrees centigrade. So, therefore, this impurity, some of silica can undergo reduction as far as the Ellingham diagram is concerned, or will remain as SiO2. So, it is a partially reducible impurity. This is a non-reducible impurity, and titanium dioxide is also, just like silicon dioxide, is a partially. It is important for us to know the nature of these impurities in order to understand that what really goes on inside the blast furnace and how the reactions are proceeding in different parts of the furnace itself. So, when you go to the mines and when you prepare excavate iron ore or bring iron ore, you have machineries so that bring in big chunks of iron ore, and those chunks, as I have indicated here, you will not be able to charge them into the furnace. So, you have to break them. So, you have to use standard setups like jaw crusher or gyratory crushers, and then you can break them, and you can, in the breaking process, some will be bigger size, because as I have indicated that we require 10 to 30 mm size range. This is the size range of the particles that we want to introduce into the 1 to 3 centimeter size. So, in one go from the big chunk you will not be able to produce 1 to 3 centimeter size particles. Some will be 1 to 3 centimeters, some will be oversized, some will be undersized. So, the exact size particles as lump ore will be introduced into the blast furnace. Oversized particles which are bigger than 30 mm are going to be again taken to crushers and crushed, and in this process we are going to generate exact size particles, oversized as well as undersized, in a repeated closed circuit combination or closed circuit crushing operation. We crush, then we sieve, then we again crush, then we again sieve, and that is why we can prepare. So, from there is no doubt that we can have exact size. In the mine itself we can have oversize and we can have undersize. These are the three possible size ranges which can come out from the mines once you have subjected the excavated ore to a crusher, and this can go directly to the blast furnace, this can go to crusher. And what we do with this? These are smaller particles, undersized particles. That means this could be, and in the process you can imagine that when the crushing is going on, you can produce even extremely fine particles like flour, atta and things like those, So, Undersized particles are going to be agglomerated, because as I have agglomerated, because unless we agglomerate the particle, agglomerate means we will cluster those small particles, undersized particles together, give them a shape, and that shape or size of the particle will come out to be in the range of 10 to 30 micron. So, through agglomeration the undersized particles will be converted to the exact size ranges, and of course those particles will also have to satisfy certain requirements for introduction into the blast furnace as I have listed here, but those requirements can be little different from the ones which are applicable to coke, for example. So, there are two techniques which are mostly used. Very fine particles, if the particles are just like flour, for example, okay, in that case we can subject them to pelletization. If the particles are little coarse, undersized particles, then we can make sinters out of those. And here that iron ore particle that I can now add, that you will have sinters and pellet also which are going to be. So, I will now briefly tell you that how sinters and pellets are actually made. Pellets are going to be made near the mines itself. On the other hand, you must understand that this lump iron ore, even the transportation of the lump iron ore, so you can imagine that if on a daily basis this sort of a material calculation you should be able to do. If a steel plant produces 20 million tons of steel, and the yield is roughly about 92% yield, you know that if you charge 100 kg and if you get 92 kg back, then the yield is 92%. So, if you assume a 92% yield for the overall plant, then you should be able to understand that how much of iron ore needs to be handled in the plant premise itself. Within the plant itself, lot of dust is going to be generated, lot of small iron ore particles are going to be generated. Even though you may be handling the exact size particles, these will undergo certain degradation, certain wear and tear, and as a result of which you can see that there are smaller particles which are everywhere. Now, very small particles, so which can be, so these small particles are really big hazards, because they create environmental pollution. When the wind blows, they are taken away very easily, and forget about charging them directly into the blast furnace where pressure is in excess of 7 to 8 atmosphere, and we have huge several thousands of normal meter cube of gas which is being pumped to the furnace, giving rise to a intensive what do you call flow conditions or stirring actions within the blast furnace. So, very small particles, and how small are these particles? This could be, I would say, in the range of 40 to about 250 micrometer size particles. These particles are going to be agglomerated and the target is we produce, the kids, as kids you might have played what is known as marbles or kancha like this. That is the size basically. So, 5 to 20 mm size spherical shaped particles are going to be produced and which will be charged into the furnace. So, how do you do it? So, we take the fines, so these are the fines, we mix them with water, we mix them with some binders, we can incorporate some limestone fines also. The moment we put in limestone into the pellet body or pellet mix, then we say we are going to produce flux pellets. Nobody uses, otherwise the pellets are basically acidic pellets because they do not contain any lime. The basicity, crudely we will introduce several definitions of basicity later on, but basicity basically we define basicity is weight percent CaO by weight percent SiO2. You can, so summation of all basic oxides, so somebody can define wet percent CO plus wet percent MgO divided by wet percent SiO2 plus wet percent Al2O3, which Al2O3 is taken. Mostly we take Al2O3, which is an amphoteric oxide, but as an acidic oxide under blast furnace environment. So you can have several definitions of basicity. Since as such this mix do not contain any lime, so basicity is going to be equal to 0. So we consider this to be an acidic pellets, but on the other hand, the moment we put in some limestone, in that case the basicity becomes finite because CO content is no more 0, and as a result of which what happens is we get a basic pellet, which we term, the exact terminology is the flux pellets. So we mix all these things, and then what happens is if we put them in a disc or drum pelletizer, so these are like you dump them, you mix them thoroughly, and then you charge onto the dim, and they rotate actually, disc or drum pelletizers, and the moment they rotate, what happens is the particles come in contact and the particles get bridged because of the presence of the water and the binder, and as a result of which you produce this sort of a small lumps. The size, and there are several mechanisms, for example, one such mechanism is that you can have one small ball plus another small ball, and that's the ball growth mechanism, and you can have one ball plus then you have the mix, and then layering takes place, and as a result of layering you get a bigger ball. So there are several ways of, basically what it is the way you make dough in your house to make chapatis, and it is exactly the same way. So you mix the right amount of water. If you do not mix the right amount of water, then what happens? You cannot make roti. If you put too much of a water, even though we cannot make roti. So once you make the dough, then you make small little what you call dough portions, okay, which you can roll out into puris, and then you can fry them out. So this is basically the same size as you would make in your house out of wet dough, those which you would like to eventually convert into puris or so. So the same mechanism applies, and what you do basically, that if you have too much of water in the dough, then you sprinkle some more flour into it so that you get the optimum. So the moisture content is extremely critical in the whole thing. The composition of the binder is very important for us. Binder amount is of course important, but more important is what is the binder is an additional chemical material, and that chemical material must not cause any hazard to the life of the blast furnace. For example, I have mentioned yesterday, if you have acidic alkali constituents, alkali binders like containing sodium and potassium, in that case you can get cyanide gases formed into the blast furnace. The refractory life can be. So bentonite is a very common binder in the blast furnace, but there are iron sulfide, iron based binders also which are available, people have been using. So the moment you find, you take the mix, you rotate the particles mixture in the disc or the drum, then after some time you are going to get some balls, okay, and those balls we call them as the green pellets. These green pellets are not fit for introduction into the blast furnace because they do not have strength. The dough, portion of the dough that you have made to for puri, they are very soft. So same is with the green pellets. They are, if you drop the green pellets okay, on the floor, they will crumble. Forget about them withstanding the load of the or the high pressure as well as the burden load within the furnace itself. So they are not yet ready for introduction. So therefore, what we do, the green pellets are subsequent step is that we will fire them, and we will fire them at around 1100 degree, so 1300 degrees centigrade. This firing will make the pellets really very, very strong. And what does the firing does really? How does it become very strong? And this is done basically in a moving grate furnace. So you have a huge furnace enclosure from which the heat is supplied. These are my burners, okay, and then you have a moving grate in which the pellets, the round pellets, are drawn. So initially the temperature may not be that high, so these are going to be preheated here, then the firing will take place and then the cooling is going. These are the regions where end effects are there, and this is perhaps the most hot region in the clean. So therefore, this as the moving grates, this is the moving part, moving grate. So you can, these are like conveyor belts, you can imagine that, okay. So and then you have discharge of cool pellets, and when, so the temperature here could be 400 500 degrees centigrade, then going up to 1200 1300 degrees centigrade, and then again cooling down to. So the intensity of burn-ups will determine that what is the kind of temperature distribution here. So this is the preheating zone. In the beginning part, the pellets get preheated, the moistures are expelled, and then comes the firing region where the temperature is 1100 to 1300 degrees centigrade, and it is here what happens is that we have various constituents which can now chemically react, and most important here is that we have, for example, iron oxide which is there in the iron ore, and that iron ore can combine with silica. Also we can have flux pellet, this is possible. Also aluminosilicate reaction is possible, and these are when this is a low melting point constituents, so they are liquid. So now you can imagine that all the particles in the green pellet, there are regions where the particles are in contact with each other, where what happens locally, some glassy substance like phyllite is going to be produced as a result of chemical nature of the constituents which are present in the green pellets. So iron oxide will react with silicon dioxide, which is present as impurity in iron ore. This is already there. You have made flux pellets, this is also there, and even Al2O3 depending on aluminum-silica ratio can also react with silica and form iron aluminum silicate and so on and so forth, and all these are basically liquid in the range of, or semi-liquid in the range of 1100 to 1300 degrees centigrade. So the moment the green, the fired pellets come here, then what happens? They cool down, and what happens to the liquid mass? This liquid mass has now reconverted into solid, and as a result of which particle to particle bond becomes very, very hard. Now the speed at which you draw this is very, very important. If if the travel time is too small and the exposure to 1100 degree to 1300 degree environment is for too prolonged period, then large amount of liquid slag can form, and as a result of which the pellet that you get here could be very, very strong, but at the end what is going to happen, the pellet may not be porous, the pellet may not have good reducibility. In general we would say that strength of the pellet, so we will say more is slag bonding. If the slag bonding, which I have explained, goes up, the strength goes up significantly of the pellet, but its reducibility goes down considerably because the pellet becomes dense, and therefore it is not possible, it will not exhibit good reducibility. So it is good. So the temperature range, the speed of the grate, okay, and the composition, that how much of lime you should be adding, how much of what should be the green strength, what should be the water, etc., and all these things are very, very important as far as determining that the extent. So you can engineer this by controlling the speed of the grate, the temperature, as well as the composition of the mix of the green pellet. You will be able to control the proportion of the slag bond, and therefore you should be able to optimize the strength and the reducibility. So I want an optimum strength coupled with an optimum reducibility for the pellet, such that the pellet can withstand, it does not undergo, and in that context there is a terminology called reaction degradation index. And because of reduction, the materials also undergo, because what happens during reduction, you started with an iron ore, you started with a pellet, but as reduction takes place, then what happens, iron oxide becomes iron, so phase changes takes place, okay, and as a result of which the density of the material, because their specific volumes are not identical, so you will expect that there are stresses which will be generated, and therefore the material is likely to degrade to some extent as reduction goes on. So therefore the reduction degradation index, how good the material is under reducing atmosphere, how good the material is able to what extent the material is able to maintain its initial strength during the process of reduction. This is an important parameter, and by controlling the final stages, okay, of the preheating and firing operations, you will be able to get pellets which have adequate strength coupled with adequate reducibility and fit for introduction into the blast furnace. So, there are more discussions, but these are pretty standard techniques. There is not much to be understood here, except that one can look into the bonds, one can look into the kinds of bonds that the water forms. So, the discussion can be taken at at a descriptive level, but I think the engineering part of the system really lies here. Having formed green pellets, how to administer adequate strength and reducibility is the crux of the problem, and that can be engineered very well, particularly in this or the later part of pellet making, which constitutes preheating and firing. So, I do not want to go to the description of pelletization. How does a drum pelletizer looks like, how does a disc pelletizer looks like, what are their dimensions? These are, I think, not within the purview of this course, because we have to finish discussing most of the critical components. So, the engineering part is also relevant, the theoretical part is only relevant, which allows us to appreciate the engineering involved in the whole process itself. So, as opposed to pelletization, which is carried out under normal atmosphere, and as I have said that pellet making operations are mostly located within the mines itself, because we do not want to transport the fines across the distance and bring it to iron plant, steel plant, and then do the pelletization. No, that is not objective, because in that process transportation of fines are hazardous for the environmental reasons. So, the second one is sintering, and in sintering we require now a little bit bigger size particles. So, this, as I have indicated, that our size here is 10 to 30 and 3 to 6 millimeter size particles, basically very small, it is chips kind of a particle which are generated. Those are going to be used in the case of making sinter. So, during the process of mining of iron ore, I mean, when you generate undersized particles, the undersized particles will be split into two halves, fine materials, and there we can again employ crushing grinding circuit in order to, because we know that lump ore is not going to be used to a large extent in modern blast furnaces. So, mostly it is going to be operated with sinter and so on and so forth. So, undersized particles, even all undersized particles may not come in this range, as well as in some particles may be, for example, 9 mm. So, it is less than 10 mm. So, what you do with 9 mm particle, that 9 mm particle will be taken to grinding circuit, okay, and then it will be ground, and in the process we will be producing 3 to 6 millimeter size, and those which are below 3 to 6 millimeter size can be ground again and then produce the raw material which is fit for making pellets. So, sintering basically in this case is a high temperature operation again. Pellets are made, as I have seen, as you have seen just now, under normal atmosphere at room temperature, the green pellets, and the firing of the pellet is done at elevated temperature. Sintering, on the other hand, is a high temperature operation, and this is done under a reducing atmosphere, and therefore coke is an important parameter in the sinter charge mix. So, we have iron ore, and the size range of iron ore is this. We have coke, we have returned sinter. I will explain. In one go, you may not convert the entire charge. Same is in pelletization also. All the fine particles you will add, everything will not get converted into pellets. Okay, you will get some pellets, some will get converted, some will not get converted, made the green pellets. Returned sinter. So, similarly, returned sinter are those portion of the charge which has not been sintered. Okay, and then we have moisture. These are in the case of, because this is done under normal atmosphere, Fe2O3 will remain as Fe2O3. There is going to be no metallization. Metallization means if from Fe3O4, Fe2O3, if we go to Fe3FeO, for example, then we say for every mole of iron there is 1.5 mole of oxygen. In this course, please note, we will use oxygen as the mole, our definition of mole, although in conventional chemistry courses you take O2 as the mole. So, we say 1 mole of oxygen to 1 mole of iron, the molar ratio is 1.5 here. We have changed the definition and it is 1 here, which essentially tells us that there is a significant amount of reduction in oxygen content, which essentially means that for the same oxygen level the content of iron is now higher in Fe. So, we say the metallization, the moment we say that we heat a pure iron, then I will say the metallization is complete. It is a partial metallization. The iron content is, the grade of Fe is improved here and this becomes 100% Fe. So, in the case of sintering, because it is a pelletization, because it is done under normal atmosphere, so we will not see that any metallization this is not possible there. On the other hand, because sintering is done under reducing atmosphere in the presence of coke, so therefore carbon can take away some oxygen, as a result of which some metallization is possible. So, these are the distinction between the two processes. Okay? And sintering is also basically done around 1100 1200 degrees centigrade, that is the operating temperature. Carbon, these are basically not carbon, small pieces of carbon which are generated, nuggets of carbon. Some people use petroleum coke also. So, this even though when you, just like the way, for example, we have made coke and and sinter making operation is in the plant as opposed to the pelletization plants which are located in the mines. So, in the plant itself we have coke oven, then we made coke, we pushed the coke out, the coke fell down, broke into pieces, we have produced many small pieces of coke. What we do with that? So, we will charge them having those size range of like this, okay, along with, so those small pieces which are generated during the coke making process can also be accommodated into sinter mixed charge, and this essentially provides the heat or the temperature because it undergoes oxidation, and we have return sinter as well as we have moisture. This constitute, and also if you have in this case we must understand the moment we have heated up to 1100 and 1300 degrees centigrade. So, even though we have added limestone in the charge mix, that limestone is going to be now calcined. Okay? Earlier the limestone will get calcined in the blast furnace itself and it will consume some heat. So, therefore, what we are now doing is that the calcination is part of limestone. So, the thermal load of the blast furnace is going to get reduced if you try to incorporate a portion of the limestone through the pellets itself. So, therefore, in this particular case also, because the operating temperature is 1100 to 1200 degrees centigrade and that limestone undergoes calcination at about 900 degrees centigrade. So, we will expect that whatever limestone we will be charging into the sinter mix, they are not going to be present in the final sinter as CaCO3, but will be present as CaO. So, you prepare a mix: iron ore, carbon, not coke, return sinter, moisture and limestone, predominantly with iron ore, and you have to do a stoichiometric calculation to find out that how much should be carbon such that the heat generated is enough. Okay? So, you should be able to the bed volume, the mass, what are to raise it to up to a temperature of 1200 degrees centigrade, how much of fuel is to be there, this sort of a calculations you have to, material balance and heat balance calculations you have to perform. Now, basically there is moving grade type sintering machines. The sintering machines are various types of sintering machines are there in the industry. Basically what you do is, the principle is like this, that you prepare a bed of sinter mix, okay, so which may be this is the principle. I am not drawing any sintering machine. Okay, so this is various kinds of materials that is there. So, you can say so these are limestone, coke, etc. Thoroughly mixed, there is no layering, they are just mixed with each other, and this, so there is a height of the bed. In any sintering machine, this is the characteristics. Now, initially what happens is, you put external heating source and you apply suction here. So, when you burn it gets heated up because you are supplying heat Q to the bed and you are applying suction. So, therefore, heat is going to be travelling downward, and as the heat travels downward, what happens is the temperature of the bed is going to be increasing. This will be much hotter than this part itself, because all the hot gas is going to be yielding its heat to this, and by the time it reaches here, the gas is going to be relatively colder. So, the top part will be hot faster. So, temperature is going to be first here maybe 1200 degrees centigrade, and after several times what happens is that the temperature here may come out to be the same. So, initially when you apply suction and the temperature of the bed, suppose you have a probe, you have a thermocouple and you have stuck the thermocouple here, and so you are going to see that the temperature is progressively increasing. And if you put another thermocouple here, you can see that the time temperature response curve will go something like this. So, this will be the bottom part and this will be the top part, that the top part there is going to be delta T lag between the two. And then what happens is, after some time, the temperature falls. Why? Because you have coke here, the charge is mixed here. So, the hot air, the moment you blow hot air passes through the bed, then what happens when a threshold temperature is reached, the carbon gets ignited because you are because of the presence of oxygen in the atmosphere, and as a result of which carbon oxygen reaction will take place and generate the heat. So, there is a heat zone here, and that heat zone is going to be travelling below as a function of time, because of the simple fact that after some time all the carbon will be burned, then nothing is going to be producing the heat. So, that layer will undergo now. It is so initially only you do this, okay, that you put external fire, okay, in order to initiate the process, but once the process starts, then wherever the carbon ignition is taking place, there the temperature is going to be higher. And where, so you will first make sinter here, then what happens, the moment 1100 and 1200 degrees centigrade will go, then what happens, the particles are going to be coming together because of the formation of the same slag bonds, or even the particles one particle can go inside another particle, okay, whereby we say that there is a recrystallization bond and there could be a slag bond between the particle. Okay? So, this is slag bond and this could be the recrystallization bond at elevated temperature. This is a weak bond. We want this bond to be there in the sinters, so that particles 3 to 6 millimeter iron ore particles are latched properly. So, the heating front is going to be travelling below as a function of time, and then at time first sinter is going to be made here, and then the sintering, or the sintering means basically it is like all the particles, you take cake mix and then when you put it in a baking oven, then what happens, that when the cake is made, you see that there are holes inside and all the wheat particles and whatever you have added, they are welded together. So, it is a sort of a cake, that is why we say it is a sinter cake. So, you will see 3 and 6 millimeter, 3 to 6 millimeter iron ore particles, they are all joined with each other, and as a result of which a huge cake can be formed out of this. Now, we must understand that because of you can imagine that if you are applying suction very fast, then in that case this carbon monoxide, carbon dioxide, carbon combustion may not be enough, or the heat may be travelling too fast, because the gas, it is a gas solid contact is important here. So, the appropriate suction is to be applied, okay, so that the heat generated, it is only the heat front should move down. I want the heat front to move here from here to here only when the carbon in this particular layer has been exhausted. But if the carbon has not combusted here, okay, and I am blowing the air too fast, then the heat zone will travel too fast, and as a result of which what happens is a uniform sintering operation will not be there. So, the suction is very important. The role of moisture is also very important, because the moisture, what happens is the moisture helps to control the bed temperature, and because of mostly the endothermic reaction, and it increases the volume of the gas also. Okay? Carbon plus H2O gives rise to CO plus H2. So, 1 mole of H2O gives rise to 2 moles of reducing gases, or CO plus H2O. They can help us in, this is an endothermic reaction. So, not too much of a moisture is necessary. We are not trying to get here a reductant, only our objective is to increase the volume of the gas, so that the bed gets heated up quite uniformly, and because we have limestone embedded in the charge, so calcination will also take place, and as a result of which CaO SiO2 bond or FeO SiO2 bonds will be created, and which will be joined together in a huge cake marks. And as I said, that the efficacy of the sinter may not be same everywhere. It will depend mostly. Some sintering machines can be very efficient, some may not be that efficient. So you will get only some part from a sinter cake which should be suitable, fulfilling the strength, reducibility and all these conditions fit to be charged into the blast furnace itself. Remaining material, what we do, we call them as the return sinter. They have not sintered effectively, their strength is not so good, so they are going to be utilized in the next round of sintering operation itself. Okay? And so therefore, the time for which you will retain this over the bed, the suction that you are going to apply, the moisture that you use in the charge mix, the amount of carbon that you use in the charge mix, these are all very critical component, and they determine the effectiveness. It is, technology is standard now pretty much. You have good machines available, they tell you what are the operating parameters, what are the but if you want to engineer, if you want to further improve it, then you have to know the dynamics of the fluid flow, heat transfer in this particular arrangement itself, and that will only allow you to design the correct suction, to design a correct material balance or correct material mix for sintering operation, and also the amount, including the amount of moisture that you want to use in the sinter mix. And also at the end of the operation, you do not want large amount of return sinter, okay? You want that at least 90% of the sintered material has got sintered. So once a big sintered cake is made, then what happens is you can break them, make into the sizes which is good for blast furnace administration, and in that process also you can produce small little pieces, and those can be charged into the blast furnace, and then the right size ones can be charged into the blast furnace, while the remaining smaller pieces can be introduced into the next circuit of sintering in the form of return sinter. These are also done in a moving grate, just like the way we have here. So you have a there are round grates actually, sintering machines, and you can have sinter beds, and the most important part here is the thickness of the bed. If the bed is too thick, if you are too greedy, you say I will make a lot of sinter in one go, in that case the sinter bed, the bed permeability, the suction, etc. are very important parameters here. And this is also, this whatever I have shown here is a stationary arrangement just to explain the principles, but in reality what happens is the sinter makers are moving grates, this kind of a scenario where what happens is they pass through different regions at different point of time. So I think we will stop. More discussion on sinter making and pelletization you will find in the textbooks. If you are interested, you can go through, okay? And only thing is that we must understand that they should have the right kind of a strength and sinters, because as I said, for example, we have introduced limestone, so therefore calcination of limestone is carried out outside the blast furnace, so it is good for the health of the blast furnace, operating efficiency of the blast furnace. Also lump ore, which is dense, has been reduced by engineered raw material which have engineered iron bearing material sinters and pellets, which are which have better reducibility. We will explain that term reducibility, and when you understand discuss in the next class about the reduction of iron ore and so on and so forth. So these are better performing materials. So I would say the last statement of the day is that a furnace operated with sinter and pellets exhibit a much higher efficiency than a furnace operated with lump ore alone. And that is why the global trend today in steel industry is that blast furnace is to be operated 100% sinters, 100% pellets are also used in the blast furnace, as the charge material lump ore has been completely dispensed with. So we will continue the discussion.